Good morning, everyone. Afternoon, evening in some places. We just have people from everywhere joining us per usual. I love seeing all of your smiling faces. Please remember that if you are enrolled in EC Engineering 19, to turn on your camera so we can see your lovely faces. That is a part of your participation here. We would love to see your faces. So please turn on your cameras if you are able. That goes for visitors as well. We are recording, of course. And we have enabled live transcription for those of you who need it. If you don't have a camera, that's okay. If your computer gets very wonky when you turn on your video, that's fine. I would just appreciate those of you who can do. No worries, no apologies necessary if you can't do it, but for those of you who can and are enrolled, especially if those of you are enrolled in the class, please make sure that you go ahead and turn on those cameras for us. We really would appreciate it. So hello, everybody. Hello, Michael, Zach, Michelle. Hi, Holly, Taylor, Sayush. Hello, everybody. It's good to see you. So we'll probably wait one more minute for people to roll into the room. We have a very exciting talk for you. We have a review. Also, just a very brief of what we discussed last week. The review that we do today will be a one-off. Not every session will get a review because that will require us bringing back every guest lecturer to give a 10-minute review at the end of class. The reason we're doing this class is because I did the last lecture. So it is very easy for me to present the review slides. I do want to make some notes for the class. Clarice, you said that the worksheet is up finally on. So we have finally put the worksheet up for you all. I know a lot of people were requesting the video. There was some technical difficulty with YouTube, but the video will be up. Both of them will be up by the end of today. So
my bad, it's a technical difficulty on my end. Sorry, people.
So no worries, absolutely no worries. We will be resolving that issue and we will make sure that everybody has everything they need by the end of the day. All the videos will be posted and going forward, they should be posted no later than 24 hours out from the last lecture. So I will personally see to that. So it is 12:04. I think it's a good time to get started, especially because I want to give our guest speaker as much time as possible. So again, welcome everybody. Welcome to the Fiat Lux, the My Favorite Qubit series. So let me go ahead and share my screen. So hello, everybody, and welcome to the Fiat Lux series, My Favorite Qubit, Quantum Computing as told by leading practitioners. This class does meet every week at noon on Zoom, and the recordings will be made available on YouTube. So, of course, for those of you who may be new here, I do want you to meet the team. There's Clarice Aiello. She is the instructor. I am also an instructor, even though I've titled myself co-instructor. I'm a first-year PhD student here with Clarice Aiello, working on magnetosensing and migratory species, basically studying magnetic field effects on cryptochromes. And we are very happy today. We have a guest, Hunter Solomon, who comes from the Colorado School of Mines, where he is working on quantum engineering, and he will definitely share a lot about his experience, and he has a great talk planned for you. Before we get into that, I just do want to go over.
My computer needs to be restarted.
Hi, if you're here, please mute yourself. Weird.
What?
Jackson, can you share co-host?
Sorry.
Yes.
My apologies.
Yes, I can. Okay, sorry about that, guys. Apologies. Sometimes that just happens. Clarice, I will make you a co-host. Thank you. Clarice is a co-host, and Hunter, I will make you a co-host just before we begin. Make co-host. Okay, now that all of that's out the way, let's go a little backwards back into our review. So I do want to start with telling you all that we do live in a quantum powered world. So we live in a world of LEDs, transistors, lasers, MRIs, magnetosensing. All of these things are quantum powered. So it's not that we have not been doing quantum computing or living in a quantum world. It's just that quantum computing is a buzzword now. So for each of us, I always love to remind us that this has been around for quite some time. It's just that it just seems more in our face because we're hearing about it more now. So just a very quick review about classical versus quantum mechanics. So remember we talked about in classical mechanics, we have predictable motions, which means that I can launch a rocket into space and I can know how fast that rocket is going and where that rocket is, as opposed to quantum that has very unpredictable motions. So I may know how fast something is going, but I can only give you a probability about where that item might be. We deal with macroscale objects in classical mechanics. So humans, human-sized things, the earth, the sun, the planets, these are very huge objects, objects that are subject to gravity. Those types of objects are the ones that we deal with when we're talking about classical mechanics. Whereas in quantum, we're dealing with microscopic objects. Some of these objects are smaller, like a billionth the diameter of a human hair. They're very tiny and they go by their own rules. Gravity does not really apply to them. So we can't use regular kinematics when dealing with these objects. And then we have classical works in continuous, where we can have, as I like to put it, the in-between numbers, the 1, 1.5, 2.5, whereas quantum is discrete packets. So there are 20 students in the Fiat Lux course, not 21.5, not 2.5 students. They are more so whole objects, whole packets of energy. So we did talk about the ultraviolet catastrophe, which is what happened when Rayleigh and Jean attempted to calculate what colors a black body would radiate at certain temperatures. And so we know that when they did their calculation, what they ended up doing ended up defying the laws of conservation. They said that all the energy absorbed into the system would emit an infinite amount of energy. And that's not correct, because if you remember that the conservation law says that the amount of energy emitted should be equal to the amount of energy that was absorbed. So what comes out must be the same amount of what comes in a perfectly conserved system, right? So their calculation gave them this infinite amount of energy, and that wasn't right. So Planck came in because he was studying the same thing, but from a different vantage point, and he postulated that a black body can only emit light in discrete quantities. So in those stair-step effects, which we'll do in the next slide, but he essentially gave us Planck's constant. And what his postulation did is that it caused the theory to match the experimental values. So he got rid of that weird infinity slope that Rayleigh and Jean were getting. So here, Planck essentially introduced quantization, which restores the conservation of energy. So as you can see in the classical, we have 1, 2.5, 3.7, all these numbers between 1 and 5 that can be decimals or fractions. Whereas in quantum, we just go whole stair steps up. So 1 packet, 2 packet, 3 packet, 4, and so. So there's no decimals, no fractions in this system. Next, of course, we went a little further back in time to, I believe, 1801, where we talked about the double slit experiment. And as you all know, this is my favorite part of beginning the conversation about quantum, because this is where all of the weirdness begins to kick in. So we talked about diffraction, which is the spreading of waves around objects, and that if we were to pass light through a single slit and observe it on a screen, remember the screen is tilted towards you, if we were to observe this light upon the screen, we would just get one line. And again, for my hardcore physicist, I know there's an interference pattern for single slit experiment, but we're going to keep it simple and talk about the just single line observation I would see if this were a flashlight on the wall. So then we talked about if we had 2 slits, what would we see? And we would get this strange interference pattern where the light would interact with itself in constructive and destructive waves. And so you would get these bands of light and dark fringes that kind of peter out or taper out on the ends. So that made sense to us. We like that. We talked about what if we changed, instead of light waves, we decided to observe individual electrons passing through the slit. And we talked about what we expected to see, which would be just two lines, because we would hypothesize that the electron would go either through the left slit or through the right slit. And what we found was that we get an interference pattern with individual electrons, which is extremely strange. So we delved into this very strange behavior, referencing the experiment done by Hitachi, where we closed the right slit but left the left one open, and we saw our single beam. All our electrons just went through the left side. Then we tried closing the left side and opening the right, and we saw the same thing. All of the electrons would travel through the right, and the left side, nothing. We did it where we closed them both, and we all agreed that the electrons are not ghosts, so they did not just pass through. We got absolutely nothing, which is, actually, I was very ecstatic about this result, because my world would have been completely destroyed if we still got electrons through no slits. And then we opened them both, and we saw this interference pattern, and we had to begin to ask why. So this began the conversation about wave particle duality. We had these electrons that were behaving in a strange way, and it seemed as if these individual particles, these individual pieces of matter, were behaving more like light waves. So we began to discuss wave particle duality, which, as I said the first time, is not a complete picture, right? Because it's the best that our language can explain these types of things. But basically, the wave particle duality is the fundamental property of matter, where matter can exhibit wave and particle behavior. So light can exhibit wave and particle behaviors. We know that with photons, and electrons also tend to exhibit some wave particle duality. The example we used is that if we had a cylinder and we oriented it in one direction and flashed a flashlight upon it, the shadow that we would create would be that of a rectangle. But if I rotate the cylinder and I flash a beam of light, then the shadow created would be a circle. And we all know that if I'm looking at a cylinder, that it's neither a circle nor a rectangle, but it also happens to be both. So this quantum strangeness also led to some new things, because when we were exploring the way these particles or these electrons were going through the slits, remember we talked about how we tried to watch it and we couldn't quite see what was going on because we had the observer effect. But before any of that happens, as the electron is traveling, it displays something we call superposition. And superposition is the ability of a quantum system to be in multiple states at once, such like a coin that's, let's say, flipping infinitely in the air, until that coin comes down and drops, until that coin hits the ground. It is only going to be in a state of superposition, which means it is going to be both heads or tails. The measurement has not been taken yet. So when we talk about superposition, now we really get into the meat of what qubits are, right? Because qubits live in a perpetual superposition state, where they are both in a state of 1 and 0 at the same time, all the time, until they are measured. And qubits are especially cool because they cannot be copied. And observation collapses the measurement of a qubit. And I think that is one of my absolute favorite sentences in all of quantum computing, is that measurement collapses. Observation collapses the measurement, because it's such a strange feat. So Hunter's going to talk a little bit more about entanglement and a little bit more about superposition. But for us, when we talked about entanglement, we talked about how when qubits become entangled, they remain connected even when separated by vast distances. So the example that I gave here was that Clarice and I each have wooden boxes, and inside the box is red and or green marbles. We don't know what color they are. So because we don't know what's inside the box, it lives in a state of superposition. So Clarice and I go to our respective places. I live 36 miles from campus. Clarice lives a little closer, but we're roughly, let's say, 40 miles away from one another. And I open my box, and the marble within my box is either going to be, before I opened it, was both red and green. But once I open it and look inside of the box, then whatever the measurement collapses to is what I will see. So I may see a red marble. In that moment, because these two marbles are entangled, because I see a red marble, Clarice is going to have a green marble in her box, whether she knows it or not. And so we know that observing a single qubit in the system causes the collapse of superposition in the entangled qubit. So that is my quick and dirty, very quick, very dirty review of our lecture. I am now going to, I've lost you all in the room. I'm going to turn it over to our wonderful speaker who has joined us today, Hunter. I'm going to give him the opportunity to, there you all are, hello. I'm going to give him the opportunity to introduce himself, tell us a little bit about himself, and go ahead and share his wonderful research with us. So Hunter, the floor is yours.
All right. Hey, thank you so much, Jackson. Hello everybody, my name's Hunter. I'm a quantum engineering master's student at Colorado School of Mines. Right now, I'm planning on doing a little bit of research in either how to do better RF or like microwave engineering systems for superconducting qubits, actually make superconducting qubits, or let's see, some theoretical work on quantum many-body physics. So that should start up probably in the summer or at like bare minimum next fall. But yeah, I have a few more slides about me in the actual presentation, so I'll just go ahead and get into it. But yeah, thank you y'all again for having me here. Okay, so hopefully this isn't timed. I usually use Google Slides, so we'll see. But yeah, title is Q the Qubit. I thought that was cute. So this is hopefully going to be a great intro for quantum computing for all y'all. So the structure of the talk, if it will change. There we go. All right. So real quick, a little bit more in depth on who am I, why you should listen to me. Then we'll dive into the history of quantum computing. After that, we'll review what a qubit is, go a little more in depth than the introduction that Jackson gave us. And after that, we're going to dive into how qubits are controlled. After that, how qubits are made, essentially a lightning round introduction to all the different platforms that you'll be studying over this Fiat series. Then afterwards, we'll get into some of the applications that qubits can be used in. It's not just quantum computing, believe it or not. And then afterwards, how you can get involved into this field, because there's a lot of ways you can, and I'm super excited to share them with you. All right, so who am I exactly? Well, I was a physics major at Vanderbilt, but I'm no longer, last May. So there's a quick little slide showing all my friends on the left. I am the third person from the back in the first one. And then also, I think there's another Vanderbilt alum here. So what's up, Ivan? How you doing? Now I currently study at Colorado School of Mines, like I said, with quantum engineering. And since I don't exactly have a photo of Mines campus, I figured I'd show you proof that I'm in Colorado with the skiing photo on the right. A bunch of us got together after graduation and did a ski trip over break. So another couple things about me. I like D&D, got into it about a year and a half ago, and got roughly 2 campaigns going. 2 player characters are really fun. But yeah, I also like being outside. And so you'll see that a little bit more of that in the next slide. So a couple other things. I like to travel a lot. I'm 23, but I've been to 30 countries so far. I did 21 before 21, and most of them for cheap too. So I'm about to ask y'all a chat out question about this, so be prepared. But real quick, the photos on the bottom. First one is in Bogota. I usually don't show that photo, but it was my first ever country that I traveled to solo. I kind of freaked out once I got off the plane, but obviously it turned out great. But that's the valley. Bogota's in a valley, and so you go up the sides and you can see a beautiful view of the city. The one on the right is, or the one to the right of it that is the La Pataya Bay at the very bottom of South America. So like where you shove off to Antarctica from. I was a crazy 21-year-old and decided that I would want to go down there because when would I ever go back to Argentina? And then the one to the right of that is Seoul, South Korea. It's the national park right outside of Seoul, so highly recommend if you ever go. And then finally, we have Kotor, Montenegro, a very underrated destination. If you ever go to Europe, go to the Balkan states. Super cheap, super good food, super pretty. So yeah. Another thing, I'm also a TA for Qubit by Qubit, which I'll get into more in the getting involved section, but essentially it's where you teach high school students how to do quantum computing, and it's been really rewarding. I'm actually finishing up the course this week. So this Wednesday and Saturday are my last labs until next August. And I'm so excited for them to graduate. And yeah, it's just been a really good time. So I have a shout out for y'all. So if you could travel to any place in the world, what would it be? And then also how much do you think it would cost? I do promise you that this is related to quantum, but I do want to blow your minds really quick for a second. And then, yeah, Clary, sorry, I didn't see that in chat. On Dungeons and Dragons. So if my slide will work, there we go. Go ahead and type your response to the prompt in the chat, but don't click enter yet. And so give everybody a few more seconds since it's not auto time for some reason. All right, and so go ahead and press enter. Let's see what we got.
Ooh, so we have Canada, a trip to Canada would be $300. We have Costa Rica for $2,000. We have France or Paris for $700. And then I also see Paris for $5,000. So a little bit of variation in how much it would cost to go to Paris. South Korea, $10,000. Brazil, $500, and New Zealand, $1,500. These are really cool answers. Brazil, Rio de Janeiro, $1,200.
Okay, all of these are pretty great. Y'all got some good options. So roughly, I did the math, and also having been to 30 countries, I got a general idea of how much it would cost. You can go to any continent, minus Antarctica, not every country, that's important to note, but any continent, at least now, assuming COVID doesn't jack up flight prices. You can go to any continent, minus Antarctica, for roughly $1,500 for a week. If you go to certain spots like Central America or South America, Southeast Asia, you can go for a month on $1,500. So in case you're ever just wanting to take a break from school, saved up money all year, you can totally do that. And also in case you want to go study abroad, that is also an option. Like, it doesn't have to break the bank. And so the reason I asked that is because there's lots of opportunities abroad to get involved in quantum that I'll talk about at the end of the talk. But yeah, keep in mind, $1,500 for a week minimum, pretty much anywhere in the world. Even Australia, New Zealand, be a little tight there, but it's doable. But yeah, if you come away with nothing from this chat out, that's what I want you to come away with. All right. So, well, now that we're done with that, oh, I also forgot this slide. This is actually the result of me trying to get my friends to go to Europe with me for a grad trip for $1,500. I had roughly 4 options for each continent to say, hey, look, we can actually do this. Like, it's doable, let's go. And lo and behold, they chose the one option that I told them would actually cost more, which is Iceland. And this is what you see. This is Siglufjordur. If you ever go, it's a remote fishing village up north. Very cute, highly recommend. Anywho, let's dive into the history of quantum computing. So the idea of a quantum computer basically came in 1979 with Paul Benioff and what we call a quantum Turing machine. So a Turing machine is essentially a basic computer. And so Benioff was like, hey, what if we can do a basic computer with quantum? So first quantum computer ever. And so Yuri Manin, shortly after, within a year, provided a more robust framework, essentially like trying to prove it, make it more like feasible, not just a pipe dream, but actually make it happen. And then Feynman, a lot of people, even potentially the speakers that you'll see in this VLX series later, will say that Feynman invented quantum computing, but that's not true, he just popularized it. So a year after Yuri Manin made the robust framework, Feynman was like, hey, this is a great idea. Let me talk about it in my talk, Simulating Physics with Computers. And so there's this famous quote, like, nature's not classical, blah, blah, blah. And like, by golly, it's a wonderful problem that you can find if you Google it right now. Essentially, he put quantum engineering and quantum computing specifically on the map. And also, if you have no idea how to read the picture on the right, essentially, it's just the quantum way to do a Turing machine. You go in a line, usually for a regular computer, like ABC, 1, D, E, etc. You keep on going, but this is saying that the quantum computer can essentially like do all of these in parallel due to superposition, which we'll dive into later. All right, and so after Feynman put it on the map, David Deutsch and Richard Jassa over the next decade helped develop the beginning quantum algorithms, so demonstrating how this could be useful. Excuse me. And because of that, you'll typically see the Deutsch-Jassa algorithm at some point in your quantum journey. And then in 1993, Umesh Fazirani and a student, Ethan Bernstein, gave us essentially the first quantum error correction code and how it would give you a deterministic advantage, or in other words, a sure advantage to quantum computers for their given applications. And so after that, something that really put quantum engineering on the map, Peter Shor developed Shor's algorithm, which essentially factors big numbers very, very quickly. And so once the governments of the world, especially the US, got a hold of that, they were like, oh my gosh, this will break our entire system. We need to develop a quantum computer so we'll stay on top of things. And so scientists were on top of it already for the past couple of decades. Then the government got on top of it and shelled in a bunch of money. And so quantum engineering, quantum computing was here to stay because of that. And then, believe it or not, you'll be able to read some of the graph on the right. This is essentially like a quantum circuit diagram for error correction. We're going to dive into most of the gates on there. So you'll be able to read it at the end of this talk. Now, in the modern day, of course, many different platforms exist that we'll go over later. And I accidentally typed that double, but pretend I didn't. However, we're still not to a full stage computer quite yet. We're at the Nisk stage, which stands for noisy intermediate scale quantum computers. We call them noisy because no stage is perfect. There's roughly 3 stages where you have the qubits, you have the gates that are applied to them, and then you have the measurement of those qubit states. And so each of those has flaws, which means that the entire quantum computer has flaws. So it isn't quite as good as a regular computer quite yet. And so one thing to note here is that different qubits have different advantages and disadvantages. And they all play us a role in getting to a full-scale quantum computer, which is roughly 6 to 10 years out. Okay, so I have a poll question for y'all. Which aspect of the history of quantum computing is most interesting to you?
Are you all able to, there we go. Okay, I was wondering if you guys couldn't see the poll. I was very concerned, but answers are pouring in. So just give it a couple of seconds and then we can go ahead and I'll show the answers. I just realized I can't participate in the poll because I'm launching the poll. So, but we hope all of you go ahead and just a few more people. Give it about 5 more seconds and then we'll go ahead and end the poll. And perfect. All right, so let's share the results. Can you see those results, Hunter?
Yes, I can see them perfectly.
Okay.
Looks like almost, okay, so everybody answered every answer, but the people managed to come up with this before the internet at 16%. So like the one with the internet, most of y'all answered, like 35% of y'all said that. And honestly, I'd have to pick that one too. It's really impressive to me that like before the internet was really a thing, like they were already doing stuff like this. Like it just goes to show you how smart people actually can be. But yeah, all the other ones are good answers as well. All right. So now that we've gone over the history, let's actually dive into what a qubit is. So a qubit is essentially the quantum version of a bit. In information theory, which is like one of the backbones of computing in general, the fundamental unit that they use is a bit. So if you slap quantum in front of that, well, you get a qubit or a quantum bit. So I know that wasn't exactly how you were introduced to a qubit earlier, but believe me, like we'll get into how that ties into this. So again, anything able to be described with quantum mechanics in principle can be a qubit, but it is a classic case of just because you can doesn't mean you should. There's several criteria for a qubit to actually like be good at what we want it to do. Namely, you need discrete energy levels. So like if there's this one energy level that we want to call the 0 state, and there's this one energy level we want to call the 1 state, they need to be far enough apart, and there's not a whole lot in between those two levels to where that if we do operations on them, we don't have to worry about it jumping to another energy level and ruining our calculations. We also need them to be easy to work with, relatively easy to gather physically. And sorry if you hear a little bit of background noise. I'm in the quantum field theory lab where I have to share space. So I apologize for that. So easy to work with. Essentially, like I know a trapped ion company was looking at trying to work with francium. So if you know anything about francium, it has a good electron structure. It's pretty heavy, which can add some advantages, but it is also very volatile and might explode on you. So despite having some theoretical advantages, realistically, it's just not good to work with. You need stuff like strontium or cesium if you're working with atoms, or you might need electrons in a certain configuration. After that, you also need to have it be easy to entangle, which is not always a guarantee. And so we also call that coherence time. So coherence is essentially how long you can keep it in superposition, and then also how long you can get it entangled with other qubits. And so I just want to give a brief review of entanglement. Essentially, like the non-quantum way I like to talk about it is if you're at a party and you're talking with one of your friends, and then another friend comes up, you essentially, that person who you were talking to reacts to that other person coming up to you, that external stimuli, and changes on behalf of that. If you were not entangled, nothing would happen. That person would ignore you. So if you imagine that you are the qubit and then your friend is another qubit that you're entangled with, the external stimuli will affect you as well as the other qubit, aka your friend. Nothing is in a vacuum. They're all talking to each other. And then another way to explain how noisy intermediate scale quantum computers work is like it's a very loud party. You try to send a certain signal in, try to send somebody to talk to you and then your friend, and they get lost talking to somebody else due to the noise. And that's another way to explain it. And then the photo on the right is of a very stylized silicon atom qubit, which we'll get into later. But this indeed is a good qubit. As I said before, not everything is. So delving into the math a little bit. Oh, I actually got a question in the chat. What is the difference between coupling and entanglement? So coupling, essentially, more or less for quantum, it's the same. Like entangling is this coupling quantum mechanically, more or less. Amirish, if that answers your question. Okay, so qubit is inherently quantum mechanical. So we decided that we wanted to represent it as a sphere. This guy named Bloch came up with it, so we call it a Bloch sphere. A regular qubit has a wave function, and because it's quantum mechanical, everything has a wave function because we have wave particle duality. And so a single qubit, or n equals 1 representation, because each qubit wave function has 2 to the n entries in it, is represented below. And in case you've never seen this, this is called Brockett notation. So Brockett notation essentially is you have, on one side, you have a line and an alligator clip with whatever you want to put inside that. And then you have your wave functions that are also a variable attached to a line with an alligator clip with whatever inside of those two things. If it's pointing to the right like it is now, that is the state that you have. That is what is actually existing. If you flip that around with the alligator clip on the left and then the line in the middle, that is the state you want to observe. And so if that state that you want to observe matches up with the function that you already have existing, that's great. It cancels out to 1 and you just get the amplitude or the variable attached to it. If it doesn't match up, then you get 0 and it goes away. So say, for example, if I attached a alligator clip 0 in a line next to the wave function that we have right below n equals 1, the 0 with the alpha in front of it would just cancel out to 1 and I would get alpha left. And then the 1 would cancel out to 0 and I wouldn't get the beta at all because the 0 didn't match up with the 1, but the 0 matched with the 0. And so to do that is relatively straightforward in practice, but once you get into like physically realizing it can be a little bit difficult, but that's neither here nor there. Like I said, it goes up to the n. So a 2-qubit system looks like this. There are 4 options here. And as you get higher and higher into qubits, it very quickly shows the power of quantum computers, because if you have, say, like 50 qubits, that is roughly 1.26 e to the 15th pieces of information to work with that you can process in parallel due to entanglement. Because if you entangle qubits with one another, all you have to do is affect one and it affects the others. And so as long as you apply a couple of gates to certain qubits, that means that you don't have to do a lot of work to process all the information in parallel because it affects every single one. And 40 to 50 qubits is roughly the classical limit that we can simulate with our best supercomputers right now. So it very quickly becomes apparent that adding more qubits to like the million qubit level of a fully commercial quantum computer that we want to have in roughly 8 years will process so much more information than we could do with classical computers. And to explain the block sphere on the right really quick, those position states with the theta and then the phi with the quantum wave function in the alligator clips, like the little candelabra looking thing, those amplitudes, those alpha and betas that I mentioned before to the left of the figure, those can be described as positions on that block sphere with like cosine of theta or sine of phi or stuff like that. As you delve into your quantum journey, just wanted to let y'all know about that. So in case that was a little bit confusing, and thank you, Clarice, for the Breca explanation in the chat. Here's a much prettier diagram representing what I just said. So on the left, you have the classical bit that can be either 0 or 1. And then the quantum bit, the superposition of the overlay different states is the position on the block sphere, aka the alpha 0 state plus the beta of 1 state. And so once we measure it, we get either 0 or 1. Forgot to mention that. But until then, everything could be everything at once. And that's how you process the information in parallel. And like it says on the right, exponential multiplication per qubit, 50 qubits is roughly 100 trillion different possible outcomes. And then massive amounts of data, like I said, could be handled because of processing in parallel. The two biggest benefits of a quantum computer is being able to process all this data and then being able to simulate quantum information properly because it's inherently quantum in and of itself. So think about being able to design a drug from scratch, being able to model an airplane in its entirety instead of just parts like the current best supercomputers have to do. If you want to run an entire power grid on one computer, technically a quantum computer would be good at that. So any huge application that you can think of, quantum computers are designed for those things. All right, so I have a poll question again for y'all. What is the most basic unit of a qubit? Or sorry, what is the qubit the most basic unit of?
Answers are rolling in. We'll give it about 10 more seconds. Keep them coming, guys. All right, we're gonna go ahead. Oh, if you're unable to see the poll, I'm unsure as to why that is. If you're not, and this is for everybody, if you have not updated to the most recent version of Zoom, there may be an issue with seeing polls and quizzes. So please make sure before next class that you update your Zoom before heading on over. I apologize if you are unable to see it. But the current poll that's happening is that we want to know what is the qubit the most basic unit of, and the answers are quantum information theory, or quantum mechanics. And so these are the results. Excuse the dogs in the hallway. These are the results of the poll.
All right, so the answer is quantum information theory. Quantum mechanics, not quite, almost. Essentially, a qubit is applied quantum mechanics, like that wave function I just described, is generalized to quantum mechanics, but we're applying it to a qubit specifically. And so it is quantum information theory. That's what the qubit is the most basic unit of. All right, so thank you all for answering that. Now that we have a rough idea of what a qubit is, let's dive into how they're controlled. So essentially, quick and dirty is that qubits are controlled by gates. You know how regular computers have gates in them? Well, quantum computers are no different. So there are many different gates, some complicated, some less complicated. We're gonna go over the less complicated ones today. So real quick, the X gate rotates 180 degrees, the quantum state that we start with, about the X axis. And the Z gate rotates 180 degrees about the Z axis. The H gate essentially rotates the quantum state that we have into superposition or out of it. depending on where it is on the block sphere. And then the C0 or like controlled X gate applies the X gate only if the control qubit is in the one state. And so you might be wondering what a control qubit is. Essentially, a control qubit is the qubit that we say that we want to look at to see if it's in the one state. And then we have another qubit that we say that's the one that's going to be affected if our control is indeed in the one state. So this is what we call a 2-qubit gate. There are a couple other ones, but this is the main one that people use because it helps put things into entanglement, which we'll see here in a second. So the matrix representation, in case you were wanting some math today, here are the matrices. I don't always remember these, so I don't expect you to, but the X gate looks like that, Z gate. The thing to note about the H gate is that it has a 1 divided by square root 2 on the outside, because if you take probability of a quantum state, you have to square everything. And so usually you get a 50-50 shot, which is why there's a 1 divided by square root 2 out there. And then the C0 gate, important thing to note is that it is a 4x4, representing the amount of potential options that a qubit has in a 2-qubit system, because that is the minimum number of qubits that you have to apply this gate. And so acting on a quantum state, we tend to start off in 0, which is why all of these start off in 0 or 0, 0. That's just convention. You don't technically have to, but there are advantages to it depending on the physical system that you're using for qubits. So everyone does it. The X gate flips the 0 state to the 1 state because that is 180 degrees about the X axis. If you start off pointing straight up into the 0 state, like on the diagram, 180 degrees just points it straight down. And so if you apply it to 0, you get a 1, and I meant to switch the other ones. If you apply it to a 1, you get a 0. And so the Z gate is essentially what we can call a phase changer. So it switches the phase of a given quantum state. So we see that if you apply it to 0, you get 0 back, but I meant to check the slide before I decided to give this talk, but you need a minus sign outside of the 1 state once we apply the Z gate to the 1 state, because it does end up changing the phase. And mathematically, you can go through that, but it is a little bit hard to understand conceptually, so it won't dive into it too much. And then thank you, Clarice, for that matrix representation. And so the H gate, essentially, if you have a 0 state, it puts it into an equal superposition of the 0 state and the 1 state. Like I said, that square root of 2 at the bottom, once you square it, gives you a 50-50 shot of the probability of having either state. And then if you apply it to a 1, the phase changes. Essentially, you get the same measurement results, but the phase is different. And so the C0 gate, as we see, our control qubit convention says that you have the control qubit on the right-hand side, or rather the first qubit on the right-hand side, which tends to be the control qubit. And so it starts off you're reading it from right to left. So if you have 2 0 qubits, nothing happens. But if you have the, sorry, this convention is different, pardon me. I keep switching conventions depending on which platform I'm on, so I get a little bit confused. But this one has a 1 in the control qubit state, and so you flip that 0 qubits to a 1 state by adding, because you apply the X gate to it. That is essentially what the C0 gate does. And also the C0 gate, as I said before, and to reiterate, helps you actually get entanglement. So we're gonna see on the block sphere what this kind of looks like. Yeah, and so say you start off in the 0 state, and 0 state at the top, and then you apply an H gate. So it points towards you, that's important. And that's what we call the plus state. You don't have to remember that, but just keep it in the back of your head. That is the equal superposition of the 0 state plus the 1 state divided by square root of 2. And so we're rotating it in the next one, 180 degrees around the z-axis. That switches the phase to a minus sign instead of the plus sign. And because of that phase change, we apply an H gate and it gives us back the 1 state because of that different phase. Usually, if you say you just start off with the H gate and you apply another H gate, like I said, you can either put a state into superposition or take it out. It would take it out, but and so since we're pointing in the other direction, but it's still an equal superposition state, it takes it out to the 1 state instead of how we would usually get it with the 0 state. So those are a couple of representations on the block sphere. Let's actually create a circuit. I know, very lightning round introduction to gates, and going from knowing what they are to 5 minutes ago to actually making a circuit with them. But y'all are smart, so I trust y'all will be able to do this. So in case you haven't heard what a Bell state was, essentially this grad student who is my age came up with these world famous inequalities for quantum entanglement that basically said, hey, quantum entanglement exists, this is real. Sorry, Einstein, because Einstein didn't like that idea of quantum entanglement. Yeah, and so here's how you create the fourth one out of all of them that he made. So you put the H gate first, essentially putting the first qubit into superposition. And then you have the C0 gate, like I said, that entangles usually with another qubit. And so now that you have a superposition state of the first qubit, you entangle the second one with it. And if you left it right there, you would either have a 0-0 state plus or a 1-1 state, because the C0 gate says, hey, if you had the 50% chance of getting the 0 state qubit, nothing happens to the second one, so you have to have a 0-0 state. However, if the first one is in the 1 state, then you apply an X gate to Q1. When if we start them all off in the 0 state, that flips it to 1. So we have a 1-1 there. But now that we add an X gate, we flip whichever one we get for the first qubit, and then we change the phase. And so that is why you see that we have a square root of 2 divided by 2, or 1 divided by square root of 2, depending on how you want to do it, next to a negative 0-1 state, and then a positive 1-0 state. So essentially, we changed the phase of the first qubit, and that gave us the first term. And then the second term was just the one that was left over before we decided to add the X and Z gate. And so if you don't quite understand this, that's okay. Really just wanted to give an introduction into how these gates worked and what you could do with them, what you could create with them. Really just to serve as a benchmark for other talks in case they mention how they apply gates. So specifically, how do you apply gates in the real world? Since we're engineers, we like a real example here. Essentially, to control for noise, we have to get most qubit types, we have to cool down to several millikelvin. So almost absolute zero, colder than outer space. And these gates are implemented in different ways, mainly by lasers and RF microwave frequencies. And optical tweezers are technically lasers, but I want to include them here because they're specifically a way to control qubits. And so you've heard before that light controls matter qubits, and then light qubits are controlled by matter. That is true. We'll delve into photonic qubits here in a second, but pretty much every other qubit platform, since it is matter, is controlled by light in some form or capacity. And so I just wanted to include this slide really quick in case you still wanted more math for whatever reason. This is perturbation theory. This is what you have to look at in junior or senior year quantum mechanics. So if this scares you, don't worry, you won't have to deal with it for a couple of years. But essentially, this shows you what happens if you poke something mathematically. And that's how my quantum field theory professor described it. So I think it's okay to describe it as poking something. It's essentially saying, hey, we know most of the function already, the correct answer, but that 1% that we don't know is bugging us really quite a bit. And so we really need to change it, need to figure it out. And so this is all the math to do that. And essentially how you control gates and control qubits is by using this perturbation theory, because each gate is technically a perturbation, but technically a giant quantum poke. So that's all you need to take from the slide. Now, the last thing for how qubits are controlled is detectors, because you got to read out the measurements somehow, right? So we moved on from qubits themselves to gates, now to detectors. So this diagram has a lot going on, but focus on the right-hand side. They have a 60 single photon detectors. Once again, those are not perfect. Those are noisy. You essentially have to cool them down to absolute zero almost as well. And so you map the qubit state onto those photons essentially, and then you read those photons out as it's being detected. And so most platforms are moving towards this type of detector. Technically there are others, but everyone uses this one. So that's the only one I'm going to mention today. That is pretty much it for detectors. There's not a whole lot going on. And then I know someone in the chat mentioned that you don't understand the math. Don't worry, I don't fully understand it either. Perturbation theory, you really just deal with. You don't exactly like it. At least most people don't. So if you don't understand it, no worries. All right, so now that we've gone through detectors, I have another chat out question for y'all. What do you think is the biggest obstacle to making better qubits, or rather just better qubits. So like I mentioned before, there are lots of different errors that could be in place on the qubits themselves, the gates, or the detection of them. So in your opinion, what is the biggest obstacle to these? So go ahead and type response to the prompt in the chat. And then don't press enter quite yet. Give people a few more seconds. All right, and then go ahead and press enter.
I think we're also new to qubits that we're not quite sure how we can make better qubits.
You're not wrong. Okay, cool. Yeah, if y'all don't have any idea, that's totally fine.
We do have, okay, so we have some things. We have controllability, errors, materials, readout, noise, talking to something cold, thermal noise on the qubit level. So we are getting some decoherence. We're getting some good answers now. Thank you guys, those of you who participated.
Yes, all right. All of those are great answers. There's essentially, I can't tell you which one is the worst one. It depends on who you ask. But yeah, the noise is the big one at any stage, readout especially, and then just the background noise, the thermal noise on qubit levels, depending on the platform, that's a big thing to take into consideration. And then, yeah, talking to something cold, like sending an RF pulse to something that's almost absolute zeros can be difficult sometimes, Zach. So yeah, scalability is definitely like a big one as well, Tingyi. So all of those are great answers. We'll touch on those a little bit in a moment. So yeah, here's another picture. I keep forgetting to flip over to the next slide, but here's some neutral atom stuff. We're gonna see this picture again, so I'm just gonna give you a taster. Now, let's dive into how qubits are made, aka the different platforms, the lightning round introduction to them for your next speakers. So as far as popularity is concerned, it does not mean that it's not popular or that there aren't people who will fight me for saying anything bad about these things, these specific platforms. But as far as what's going on the absolute scale, it goes from few people to a lot of people as far as least popular to most popular is concerned. And so on the least popular side, we have nuclear magnetic resonance, and then it goes up to nitrogen vacancy centers. Then we have silicon quantum dots. Finally, we're getting into stuff that you'll see like quantum computing companies do. We have neutral atoms, and then trapped ions of photonic qubits. And then finally, perhaps the most popular of all, superconducting. And so since we're running a little bit out of time right now, just do a lightning round introduction. So NMR qubits, I wish I knew more about them, but unfortunately I don't. They essentially are the spin states of molecular nuclei. Spin states essentially, spin is a quantum number a quantum variable that you can account for. And that is part of how chemistry works as well, in case you're like looking at probability clouds and all that. But anywho, use the spin states that are available in molecular nuclei. And the advantage is that it's a great teaching tool. You can have a few qubit quantum computer for pretty cheap, and you can illustrate quantum weirdness with it, simulate it really well. The problems are that it has a lot of noise. Out of all the problems that I mentioned before, this one just has them exacerbated, cranked up to 10. And so it was recognized early on that a lot of people probably wouldn't be using this for anything more than just basic teaching tools. However, there are a lot of people that like this tool, like this type of qubit. And so you may see in a few years a lot of groundbreaking research that makes it pop straight back into the forefront. Now we also, moving on to something that actually holds a lot of promise, nitrogen vacancy centers. Essentially, you use the electron spin inside diamond defects. And if I get any of this wrong, please correct me. But the advantages are that there are good coherence times and that you can more or less do it at room temperature, which is really nice. Instead of cooling it down to almost absolute zero, you can just do it in your room. That saves a lot of money because dilution fridges cost anywhere between 100,000 for like a 1 qubit dilution fridge to a few million for a robust one. So to do it at room temp, great advantage. Disadvantages, however, not very well developed yet. They show a lot of promise, so that it's only going to get better. And then they are, because they are in diamonds, a little bit harder to scale than other methods that you can control for a little bit easier. Oh, let me read what Clear's put in the chat. Oh, cool. Yes. First quantum computing implementations were on nuclear magnetic resonance. Unfortunately, they haven't advanced quite as fast as they probably should have. Yeah, so moving on, we have silicon quantum dots. So you'll see spin a lot here because spins are a quantity that are very separated from each other. So you can map one to the 0 state and then the other to the 1 state pretty easily. We have the nuclear spin of silicon atoms. And so the advantages, it's a familiar material. You know, the whole computing world is made of silicon, and we've gotten good results so far. So why not continue to use it? Disadvantages are that it's not well developed yet. But since everybody likes silicon, it's only going to get better, most likely. Now, moving on to cold or neutral atoms. We have atoms stripped of electrons and then repurposed to be whatever the computer wants them to be. Advantages is that in theory, it's a simple concept, and you can more or less do it at room temperature, and there's good coherence times. But in practice, it's hard to make patterns with these things because you have to use optical tweezers to manipulate each and every single qubit one by one, unless you have more optical tweezers to work with than just one of them. And so, in other words, there's a lot of moving parts. And when you include a lot of moving parts, great things can happen, but it is very complicated. So you'll see companies like Atom Computing or Cold Quanta start to like really make strides in this neutral atom technology, but there's still a long way to go to like scaling up, essentially. Now we're getting into some of the bigger players. We have photonic qubits, and yeah, it's just photons, you know, particles of light. The advantages here are that it's a familiar particle. So, you know, people have been studying photons for forever. That's part of the ultraviolet catastrophe. And then they kind of can be at room temperature. Essentially, the detector that they use needs to be cooled down to several millikelvin. So it's not really room temperature, even if most of the device is room temperature. And then the disadvantages is that qubits really don't like to entangle with one another. They don't like to talk to each other. They're kind of persnickety about it. It's really hard to get them to communicate relative to other qubit platforms, at least. And then they're limited by chip size because since light qubits are controlled by matter, these photons run through a path on the chip itself, and it's limited by just how big you can make the chip. And once you get to a certain scale, sizing constraints really start to take over, and it just becomes a complicated mess. So Xanadu right now is a company that's working on this, but they're still lagging a little bit behind compared to other companies because of that chip constraint. Now, honestly, my favorite qubit, if you had asked me, it's just ions in a line or a circle, depending on new platforms they may be coming out with. You essentially trap a specific type of ion that is reasonable to work with into an electromagnetic water bottle. As you can see in the diagram there, that's what the line of ions is in. And that like phasing light that is coming up from the bottom is the detector. And you can see two lines on the diagram there. Those are lasers. Essentially, you play this like a piano. That is how cool this is. You send coordinated laser pulses to each of these ions to make them like perform gates. Like a single qubit gate is just one laser beam pulse. C naughts are like two laser pulses put together. And then IonQ specifically, one of the biggest trapped ion companies, I think just made a 3 qubit gate. So 3 laser pulses, or basically like a chord on a piano. It is super cool in my opinion. And I wish I could talk about it more, but I have to defer that to your next speaker. So a couple of advantages are that this one is the least worried about losing any qubits, because once you trap the qubits into the vacuum that it's in, and then the electromagnetic water bottle, you usually don't have to worry about them for 6 months to a year at a time. And if one does inevitably escape, you just refill it. Simple as that. And it's not as cold as superconducting qubits. You do have to cool it down to, I believe, maybe 10K, but that's a lot better than several millikelvin. So relatively speaking. And then gate fidelity is high. You can apply gates to them pretty well compared to other qubit platforms. Disadvantages is that because it's a bunch of ions, it is hard to scale. And then like neutral atoms, even though a little bit less, there are several moving parts. So it just becomes more and more complicated. Oh, sorry for that, Clarice. Gate fidelity essentially is like how often your gate performs the way you want it to be. So if you want to apply an X gate, how often does it actually apply an X gate instead of doing its own random thing and ruining your calculation? Fidelity is like how the non-quantum way I like to think about it is like a golden retriever. It's loyal. It always does what you want it to do. It never betrays you, essentially. That's what I think of fidelity as. Essentially, it's how confident you are in a calculation. So high gate fidelity means that you're very confident that this gate is applied as you like to apply it.
Hunter, just very quickly, I know the class is only slated to 1. For those of you who are still here, we thank you. We'll be wrapping up shortly. I know Hunter doesn't have a whole lot more slides. So just stick with us. If you do have to leave because it conflicts with another class, we will be posting the recording again, so you're welcome to go. But for those of you who are staying with us and sticking it out with us, it won't be too much longer. We're just gonna go through a couple more things. Thank you so much. Go ahead, Hunter.
All right, awesome. Thank you for letting me know. So yeah, I'll blitz through superconducting qubits really quick, and then the applications and how to get involved, and we'll be done. So I forgot to change this again. Forgive me. Yeah, so superconducting qubits, they're not ions in a line. They're actually pairs of electrons put together in a chip that you see on the right. And then the reason why you see this crappy photo on the left is because it's super, super, super easily scalable. And it's so easily scalable for superconducting qubits that I, as a grad student, can make them, and you, as a freshman with a semester's worth of training in a clean room, can make them. Those aren't actually superconducting qubit chips on the left. Those are crappy MOSFETs, which is another electrical engineering structure. But essentially, the only thing you have to change there is changing the mask or like the pattern that you etch onto there, and you have a superconducting qubit. So it uses technology that's already been available for a few decades. So it is super, super scalable. Once again, you could do it yourself in a semester if you really tried. And then superconducting qubits are great for error correction. Disadvantages is that they have to be cooled down. It doesn't work otherwise. And that despite being great for error correction, the qubits aren't always super good. So there's a big irony in that. But that's superconducting qubits in a nutshell. Because we're running out of time, I guess I'll skip the poll. So hopefully you have a rough idea of what the qubits are right now. My favorite, not biased at all, is trapped ion quantum computing, but I digress. So let's get into the applications really quick. Pretty much there's a lot of different ways to use this, not just quantum computing. You have quantum sensing, atomic clocks, and then quantum internet. Quantum computing, not really much to be said here. We went over it already, but think any huge application like designing a drug from scratch, designing airplane parts, cracking current encryption methods, anything crazy, quantum computing can handle that more or less. So quantum sensing, something I just want to throw these out there. You have stuff like inertial sensors, which essentially would eliminate the need for GPS because it would calculate your inertia as you go and your position on the Earth's surface. You also have gravimeters, which can see really deep into the Earth's surface or into man-made structures just by detecting gravitational differences. You also have electromagnetic sensors, which think MRIs on steroids. You also have LIGO, which is a gravitational wave interferometer. Oh, perfect, Clarice, awesome. And so you have a lot of different options for sensing, but they all use qubits, or they can all use qubits. Gravimeter on the right, and then LIGO on the left. So anywho, atomic clocks, kind of what Clarice mentioned. They're the best clocks we've made. If you ever want to keep time, use an atomic clock. It's essentially a helper to all other applications. For example, I think one of the world records for the best atomic clocks that keep beating each other is at UC Boulder, or CU Boulder rather. And it is so sensitive that it can detect gravitational disturbances in the gravitational waves. And so it became a space-time sensor by accident. Essentially, if you have an atomic clock, it's a great multi-purpose tool. You can use it in pretty much whatever. And so finally, we have quantum internet. Essentially, this is what people want the next gen internet to be. You have a giant network of quantum computers talking to each other, potential for enormous exchange of quantum information, whether that be experimental data for designing drugs or modeling molecules or secure communications for whatever purposes. It's just what the next gen internet that people want it to be. And so think just transmitting a bunch of information. And so you usually use photonic qubits for that. You can also use nitrogen vacancy centers. Those have networking applications as well. But yeah, so last couple slides here. How can you get involved in quantum? So there's a lot of different ways, actually. I had you answer that poll at the very beginning, or rather chat out at the very beginning about where you want to travel. Essentially, if you want to travel abroad for a study abroad program, there's a bunch of different universities that are offering quantum engineering courses now. For example, UNSW, or University of South Wales, I think in Sydney, just offered a year or two ago a bachelor's of engineering in quantum engineering specifically. So if you ever want to go to Australia, you might be able to actually take quantum engineering courses. You can also study abroad in Europe. They have courses for that as well. Pretty much anywhere English speaking, and then probably elsewhere that isn't English speaking as well. And so the reason I asked you about that original question was just because I wanted to show you, hey, you don't have to break the bank. I highly encourage you to study abroad somewhere. Then you might recognize the picture on the left. That is, of course, your school. There's a lot of different research you can get involved in at UCLA, I'm sure. I know Clarice is involved in the field. So if you ever wanted to learn more about what she does, I know she'd love to talk about it. QEDC, if you haven't heard of them, that is essentially the very first place you need to go for quantum internships, quantum jobs, quantum info. It's the Quantum Economic Development Consortium. And it just has a lot of good info. And I have a few links on the next slide. And then finally, qubit by qubit, that, the teaching high school students about quantum computing, the thing that I'm a part of, highly recommend. For one, it's good on your resume if that's all you care about, which no judgment. But two, it's just a great way to teach people about this new field. Teach high school students, they're eager to learn. They tune in from all over. You get to hear a bunch of different things about what they're doing, whether they're learn Pakistani cultural things or learn about finance from a Russian senior. You just learn a lot of cool things, get to meet a lot of cool high school students and teach them about a wonderful new field. So if you're ever interested in that, please email me. Love to talk about it. But yeah, that is all I have for y'all. Here are a few links that I gave Jackson earlier. My email's at the bottom.
They're all in the chat as well. So if you want to copy them and paste them somewhere before the meeting ends, everybody, they're all there.
And then they'll also be on a PDF. I'll share this with y'all shortly. So yeah, thank you all so much for having me. And that's all I got.
Thank you so much, Hunter, for the talk. We appreciate having you. For those of you who are still here and do have time, if there is anybody that does have questions, concerns, or observations that they made throughout the presentation, please feel free to unmute yourself and ask your question or throw it in the chat. We'll do that for the next few moments before we completely dismiss. So are there any questions, comments, concerns, and or fears that may have come from the talk on quantum computing? Hunter, I did note there was, I think earlier, someone had a concern. Thank you, Shivani, about the matrix, one of the matrices.
Yeah, okay. Go back there.
And they said that they were concerned there was a typo in the X gate in the third column, maybe down in C not.
Oh yeah, so there are typos. I apologize for that. I accidentally had to have a surprise surgery on Saturday, so I didn't quite get to comb through these as much as I wanted to. But yes, for example, the Z gate right here definitely needs a minus sign out here on the right hand side. You said there was a typo with the X gate. Yes. I switched the 0 and 1 on the second one. That should be, if you apply X to 1, you get 0 state instead of just repeating myself. So,
and for those of you who had that concern, we will make sure that is corrected when we send the PDF out to you all. So no worries. Thank you for bringing it to our attention because of course, I know a lot of people are new. So we do want to note, including in my presentation, note all of our mistakes so we can make sure that the information we provide to you is accurate and complete. So thank you, Hunter, for that. He will be making the changes to the gates and the convention changes that he made mid-presentation
Yes.
so that everything will be cohesive when you all see it again in PDF form. Where
Yep.
there, we have another question. It says that I am curious how long it would take for QC can be used to help with climate change and other aspects of social impact.
Yeah, great question. It really depends. Quantum computing can be used as a platform to like educate people, get a bunch of diverse individuals into the field. And that's a great way for social impacts. For climate change, the big thing I can think of right now is solar cells are inherently quantum. And so being able to model them effectively would really help speed up their efficiency. At least that's the hope with a quantum computer. And among other things, better climate simulations, more robust climate simulations can really help us try to figure out what our actions on this earth might cause. And so that's off the top of my head, those are a couple of ways that I can think QC can be used to help with climate change.
Thank you for that. Are there any other questions from the students, participants, visitors? All right, well, if not, thank you all for joining us today for our Fiat Lux seminar. We hope to see you again next Monday with our new speaker. We will be releasing these PDFs shortly, and of course, all the YouTube videos will be up by the end of today. Thank you all again so much. Thank you for staying the extra time.
And I just want to thank Hunter personally because he had a hard time this weekend and he still made time to talk to us. So thank you so much. We really, really appreciate it. We're very grateful.
Thank y'all for having me.
All right, thank you all. And Clarice and I will stay on. Hunter, you are free to roam about the country if you'd like, or you can stay and class is dismissed.
All right, awesome. Well, y'all have a great day.